favorite quote that propels me to take action in life says, "You miss 100% of the shots you don't take." Let us take our shot of velocity versus time graph by doing lesson 3. The velocity versus time graph of a free falling projectile is drawn using the equation of motion that says final velocity is equals to the initial velocity plus the acceleration due to gravity, because we are dealing with a free falling object here, times the time that it takes to move in the air. If we rearrange this equation so that it has the final velocity being equal to the acceleration due to gravity times time plus the initial velocity. What I've done here is that I've just taken this term and actually have put it in the front. It is still positive there really. And I've taken this positive term as well and have placed it behind. This makes us to realize that there's similarities to this equation when we compare it with, let's say, a function g of x is equals to mx plus c, because we can clearly see that the g of x is actually the same as the final velocity of the projectile, and the m here, it is the same as the acceleration due to gravity. The same is true with the x. The x here is the same as the change in time, and our c here has the same properties as the initial velocity. What we are observing here is that this equation is actually a linear equation. It's a straight line equation. This equation of motion here is a straight line equation, and that already tells us or makes us to conclude that when we draw our velocity versus time graphs, it has to be a straight line graph because it is defined by a linear function. We are saying here that g of x is equals to the final velocity. The m is the same as the g. The change in t is the same, or rather, let me write it in this fashion. They are the same really, but I just want to write them starting with the function here and going to our equation of motion. So the x is the same as the change in t, and our c here is the same as the initial velocity. Now let us look at the properties of each of these terms, or other variables in these two equations. When we look at the g in this equation of motion, we said it is the same as the m. The g, we know from a straight line equation that it is the gradient or the slope of the graph. So that means our g on the equation of motion will be the slope or the gradient of the position versus time graph. Remember, we said this will be a straight line, so it will be a straight line that has the slope defined by g. The slope we know from studying mathematics, studying functions in mathematics, that it determines the shape of our graph. That is to say, it tells us if our straight line is going up or is going down. How do I mean? When our g is positive, in other words, when it is greater than 0, if we get a g that is positive, the graph will go uphill. That means that our graph will be a graph that goes uphill like this. Because our g would be greater than 0, it will be a positive g. Now this already automatically tells me that the direction that we are dealing with in this instance would be a downward direction being positive, because we know that if I draw a vector of the acceleration due to gravity, it will be a vector that goes vertically downwards, and it will be a vector that has a value of 9.8 meters per second squared. Now, because it's a positive value here and it's a vector that goes down, it then means this direction of going down is a positive direction. Now, it is also true that our g can be negative, in which case this means that our gradient, because g is the gradient, remember we said g is the gradient, is the m here, our gradient would make this shape or the graph to be downhill. That is to say that our graph will then now go downwards like that, because a negative slope, when our slope g is less than 0, meaning negative, our graph is expected to be a graph that goes downwards like that. In the same way, this would automatically mean that our direction of going downwards is negative, because yes, our acceleration due to gravity always goes downwards. That's why we always talk about the direction of going downwards, and we are saying here that our g is negative, so it's a negative 9.8 meters per second squared. It's negative here because our slope is negative, so that means it's going to be negative 9.8, because already we know it's a constant, this number. Now, because g always goes downwards, it then means down here is then chosen as negative. That's why this g is negative, and the graph will be in such a way that it goes downhill. The second property that we'll look at here would be the c on this graph. Remember, the c is the same as the v initial, the initial velocity of the object. Now, this initial velocity here, we know from this equation of a straight line that the c here stands for the y-intercept. That means on our equation of motion, the vi should be the y-intercept. It should be the y-intercept of the velocity versus time graph. And we also know that the y-intercept, if we want the y-intercept c here, we get it when the x is 0. In other words, if I put 0 here, I'll have this whole thing becoming 0, so that now I have only c left. And that means my coordinate would be a 0 and a c. Now, in the same way, when we look at our equation of motion, it also means that this y-intercept will occur when the time is 0, because the whole thing here will be 0, so that now we actually have a coordinate 0 and v initial as the intercept. And remember, the intercept is a line that cuts the vertical axis, the y-axis. So the y-intercept occurs when the change into 0, and this means that this is when we start our motion, because the time will always be 0 when we start our motion. And it makes sense a lot, because vi is when we start our motion, so it occurs when the time is also 0. And automatically, when I'm speaking around these things, you already can see that our change in t is really x, as we have said, and it's simply going to be the independent variable, and it is drawn on the x-axis. Now, what I mean by this is that if I were to draw my Cartesian plane like this, my axis of Cartesian plane like that, I would have my t measured in seconds to be along the x-axis, because it is the independent variable. The only variable that's left now is the g of x, this guy here, which we said is the same as the v final. Now this is a function of x. G of x is a function of x. That's why we actually write this in brackets to say there's an x in there. It changes, the value of g of x, it changes as x changes. In other words, when I put different values here, it will influence the whole thing here, which is g, what value I get after changing that value of x. The same is true here to say the final velocity here is actually the function of time. As we change time, it will influence how this whole thing will change, because the intercept will be a constant. It won't change. The number that cuts the y-axis, and g also is a constant, 10.8. So the only variable that's changing here is the time. So as we change the time, it actually influences what velocity we get. This is the reason why oftentimes than not we always write this v, the final velocity, as v, because it occupies many different values as the time changes, So sometimes we represent it by the letter v. Now that is our velocity here, is the velocity of the projectile at any time during the motion of the projectile. And as I said, it is the function of time. It depends on time, and that means it is plotted on the y-axis because it is influenced by the time as it increases. Also here we'll see what happens. Will this decrease or increase? So that means here we're going to write v because it's a variable that will change as time change and is measured in meters per second. Remember that this is the velocity, that's why we're measuring it in meters per second. And very important, it is the velocity, not the speed. In other words, direction will be reflected when we draw our graph. The values that we read here, the positive values here, will imply a positive direction, and the negative values here below will imply negative directions. So here we have the origin as usual in our Cartesian plane. The origin means a point where the time here is 0, is a point where the time is 0, and also is a point where the velocity here is also 0. That means going here and going up, the velocity is actually increasing, and also going here, going down, the velocity is increasing. The only difference is that here it's getting positively large and this side is getting negatively large. That is, it's getting negatively large. That is to say, here is going to the positive direction and here is going to the negative direction. And our time is always positive because time is a scalar quantity. We always measure it to be positive. We don't have an axis here that shows negative time. Now, let us use all this information to see how to sketch, or to learn how to sketch, velocity versus time graph. We are going to do that by looking at question 1 here. So these are like example questions that help us to be interactive in learning how to draw these graphs. The question reads as follows: a ball is thrown vertically upwards with an initial velocity vi from the edge of the balcony, and after reaching the maximum height, it returns to the reference point. So we're saying we're throwing a ball from this point, it goes up, reaches the maximum height, it then returns and comes back to the balcony, and we say the balcony is the reference point. That means that's where we measure our 0 position. That's where we start measuring our position. And this reference point is the same as the initial position because it's a position where actually the projectile starts moving. The question further says that ignore the effects of air friction. Now, this is to say that this object, when it moves in a free fall motion. That means the only force that is acting here is the gravitational force. And that is a normal case for vertical projectile motion, it becomes a very specific and unique special type of motion, because this motion can get complex when there's air friction and other things, external forces. Then question 1.1 says to us that draw a velocity versus time graph for the ball. So we are drawing here a velocity versus time graph for the ball. We are told to also choose direction such that down is negative. I'll start first by writing my reference frame here. So a reference frame is a set of axes that show direction. Now in my reference frame, I'm saying that if there's a vector that goes in this direction, meaning to the right, will be positive, and that means a vector that goes to the left will be negative. And I'm also saying that if there's a vector that goes up, it will be positive, and if there's a vector that goes down, it should be negative. And that's what we were told to say, down should be negative. So by saying down should be negative, it means up is positive because it's the opposite direction. It is conventional to always write the x part of the reference frame here when we choose direction, even though in this specific question we are not going to use the x part, but it's just a norm to write it. Do not get confused by it. Now after we have chosen direction, you would notice that when the ball is here, that's where it begins its motion. In other words, it will have an initial velocity here, which will be a positive vector because it is going in the positive direction there. Now the ball will then continue to go up, perhaps reaching a height somewhere here or a position somewhere there, because it is now moving from zero position going upwards. When it gets to this position, you will note that our velocity would be I want to draw this carefully because there's some details that we need to discuss here. It will be a vector that is going upward like that. Now notice that this vector here that I've drawn is smaller than the vector that we started with, the initial velocity. And I'll call this V1, and also it's going in the positive direction because it's going upwards. Now this vector here is small compared to the initial one because when the projectile goes upwards, it's actually slowing down. Now if the projectile continues to move, it will get to a point where it reaches this height here, the maximum height. And actually here we don't have a vector because the velocity at the maximum height, Vmax, is equals to 0 meters per second. Remember that the projectile is slowing down as it's going up, such that when it reaches the maximum height, it will actually have a 0 velocity because it was slowing down as it's going upwards. At this stage, it will stop for an instant, for a very short time, before changing direction and going downwards. Now, when it goes downwards, it will occupy the same positions that it was occupying when it goes up. So that is to say, at some point, it will come back here at this position. Remember, the projectile literally goes up straight and comes down straight. It does not necessarily follow this path here. We just draw this path so that we are able to explain these vectors that are taking place. So the projectile will come back to this height exactly on this line when it goes down. But this time you must understand that it is going down so that our velocity will now be pointing downwards. And we are going to have velocity 1 here, meaning the magnitude of the velocity, this length here, is the same even when it's going down because of velocity speed symmetry that we spoke about. The only difference is that this velocity is negative. So we have the same velocity when we go down as the velocity that we had when we're going up, except that the direction is now in the opposite direction. So the speed is the same here. The magnitude of the velocity is the same, but the direction is different. So the velocities are not the same. The projectile will continue going down, occupying the same positions that it did when it went up until it reaches the balcony again. And here on the balcony, it will have the same speed that it had, VI, when it was going up. But the velocity is going in the downward direction. So same magnitude of velocity, but in the opposite direction. So that is to say this length here is the same as this length, but the direction is different. Hence this arrow is going up and this one is going down. The velocities are not the same, but the magnitude is the same. Now, during this motion, whether the projectile is going up or going down, we always have the acceleration due to gravity going downwards. Like that is a vector that actually goes downwards like that and is defined by g is equals to 9.8 meters per second squared. Because we chose down as negative and this vector is going downwards, it's going in this direction, it will then be a negative 9.8. The reason why the projectile was slowing down as it goes up is because of the velocity vectors that are going up are actually in the opposite direction to the acceleration vector. The velocities are going in that direction, the acceleration is going in that direction. Therefore, the object must slow down. Hence, it stops here at some point and comes back down. Now, when it goes down, you'll see that the velocity vectors are actually in the same direction as the acceleration. That's why when it goes down, it's actually speeding up. It's regaining the speed that it was losing when it was going up. Now, let us translate all this information into a graph and sketch the velocity versus time graph. Well, the first thing that we have to notice is that the y-intercept here is actually given by VI, positive VI. This initial velocity here is the y-intercept. Remember that we are using here the equation that we just did here at the top. I'm just going to draw a line here so that we do question 1 properly. We are using the equation V final is equals to G times change in time plus V initial. And we are saying here that we have negative 9.8 multiplied by time, and we have here positive VI. Remember, this VI here is positive, so we have a positive VI there. Now, this means that our graph has a gradient, has a slope, a negative slope. We have here a negative slope. Our slope is negative. The M here is negative because we can see that our direction of downwards is negative. This means that our graph should be a graph that goes downhill in terms of shape. It's a graph that should sit like that. That's the first thing that we notice from this equation. The second part is that we look at the y-intercept, which is given here by VI, which is positive. So our y-intercept is positive. That means our graph should cut the y-axis in the positive side of the Cartesian plane. And remember, the y-axis would be a point here on this graph where we start to draw our graph. It is the point on the far left. Now let's put this into a sketch. I will say here I'm drawing a velocity versus time graph, V versus T. And I'll draw my axis of, I'll draw my Cartesian plane, my x-axis, which is given by TS, and my y-axis, which is given by V, is measured in meters per second. And we know that this is the origin. That's why the velocity and the time are both 0. Now here you literally take this line and put it on the graph. But when you do so, you'll realize that when the time is 0, when our time here is 0, we actually plot a point here that is given by positive VI. Because our VI is positive, we said it is the y-intercept that should be on the positive side. And that's where our line starts. As I said, is a point here. That means this point will be translated here and the graph should go down like that. So I'm going to draw a line that goes down like that. And we can see that this is a line that has a slope that is negative because it's going downhill, and it intercepts the y-axis at the positive VI. Now, when we look at this graph, we can see that when the time is 0, we have an initial velocity. We have initial velocity here of VI. We plot VI here. This is at this point here. When we start pressing our time, it measures 0, 0, but the velocity is VI because that's where we start throwing the ball. At some point later on here, when the time has increased, we actually measure T1, maybe the time from 0 to here, T1, and that time it actually gives us a velocity here, which we called V1 and is positive. So this is the velocity here. Notice on the graph that this velocity is small compared to this velocity because we are going down now. And that's what we said, to say the initial velocity here would be bigger than this velocity here, because as it goes up, the velocity gets smaller. The speed gets smaller in magnitude. The velocity gets smaller in magnitude. Our speed is smaller as the ball goes up. And we see that in the graph. And you can see that this relationship will continue until some point here where we don't have speed anymore. So we'll have some time t here. And when we measure that time, we see that our speed is actually 0. And this is actually this point here at the maximum height where our velocity is 0. So when we reach that point, we'll be at V max, meaning the velocity at the maximum height will be 0 now. And this would mean this is the time at the maximum height, T max. Past this point, the time will continue increasing so that now here we have T3, I'll call it. And at this stage, you can see that we will measure a velocity that comes out to be negative here. And you have to note that because of symmetry, this velocity has to be the same as this velocity here. In other words, it has to be V1 as well. It will be exactly the same speed, the magnitude here, but it points in the opposite direction. So this is positive, this is negative. And that's exactly what we actually observed here, to say we'll have the same speed, but it points in the opposite direction. The velocity points in the opposite direction. And the same will be true if we continue measuring time at that point there. We'll have T4, and it will measure some velocity here, which will be a negative V initial. It will be the same magnitude, this velocity, as what we started with, because, vertical projectile motion is symmetrical. The velocity here is the same, but they point in opposite direction. So this one was positive and this is negative. Now, if you have been following what I've been saying here, you'll come to realize that this part of the motion, let me perhaps get a different highlighter, because I see the one that I took has the same color. This part of motion here would represent when the projectile is actually going upwards. So this is upward motion. And this part of the motion here will actually represent when the projectile is really going downwards. And we can see that the time that it takes to go up here will be measured or be given by T max. So we can write this time as T max, meaning the time it takes to go to the maximum height. And also from here to there, we'll get the same time T max, because it takes the same time to go up and to come down. So here we'll measure the same time T max. So these two take the same time to move actually up and down. So that is to say that this T4 can actually be rewritten, or I can write it as T total, meaning it will give me the total time that the projectile takes to be to go up and down, because remember, after this point it is at the balcony, it is not moving anymore. So that means our change in T total will be the same as, let me create space actually so that I can write this equation properly. So here I'm saying my change in T total, meaning the time here that we read here, will be the same as change in T max, right? The change in T max here plus the change in T max. So I'm adding again the change in T max because the time it takes to move here is the same as the time it takes to move here. So we can just write them as T max because they're really the same value. That is time symmetry, as we have discussed it in our first lesson when we introduced vertical projectile motion. Now here you can see that these two will actually give me 2 change in T max because I'm just adding like times there. So to get the total time is the same as multiplying the time that is here twice by itself, or you can add them if you like. It will depend on the problems, what information you are given. I hope that this analysis and approach of drawing these graphs makes sense to you. The next question, 1.2, says to us that we should draw the position versus time graph again. The velocity versus time graph, I meant to say, but in this case we take down as positive. In other words, we change our direction. Let me erase here so that we can look at this situation. Now what we are saying here is that we choose down to be positive. We say vectors that go towards the downward direction are positive. That already tells me that if there's any vector that goes up, it should be negative because it's the opposite direction. Now you would see that when the ball is here, our initial velocity here, I'm not getting a straight line there. I want to draw a nice vector that goes up like that. We can see that our initial velocity VI would be negative. Why? Because it goes upwards, and we're saying downwards should be positive. That's the only thing that they're changing. When we change direction, everything else that we had before, it will still be there, but the direction will be changed. And this would also mean that the projectile will then go upwards, occupying smaller velocity until it gets to the maximum height where there's 0 velocity. Then it will change direction and have velocities that are going in that direction. So this is to mean that the velocities when it goes down are now positive because they go in the positive direction. So I'm only going to draw this one when it gets here. It's going to be a positive VI. It is VI because speed is symmetrical. The velocity that we go up with is the same as the velocity that we go down with. They're exactly the same. And not only here, but at every point that the projectile reaches. I'm just drawing these two. Now we also know that the acceleration due to gravity will always be present, and it will be given by 9.8 meters per second squared. In this case, it becomes a positive velocity because it goes in the positive direction. Remember, now we're saying down is positive. Now this means our 9.8 will also be positive. So we have enough information at this stage to actually draw this graph. I will say now I'm doing 2.1. We are drawing velocity versus time graph. Now when we want to draw this graph, the first thing that we have to realize is that the gradient is actually positive. That means our graph should be uphill. We expect to have a graph that goes like that. And we're also saying that our y-intercept is actually given by a negative VI. Do you see that our initial velocity, that the ball goes with, that goes upwards, is actually negative. And we know from that equation that this is the y-intercept. So what I'm saying is that if I were to rewrite our equation that we use to draw a straight line equation, it will be v final is equals to change in t plus vi. Now if I substitute here, I'm going to have a positive 9.8 times change in t, but here I'm going to have a negative vi because our vi is negative. Our initial velocity is negative because we chose down as positive in this case. That's why we have a line that should go up, but now our y-intercept will be in the negative part of our x-axis. It will cut the negative part. Now when we draw this sketch, we are going to have our set of axes where we have the independent variable to be defined by time and the dependent variable to be defined by the velocity, and here it's 0. This is standard procedure. You always have to put this. You can't lose marks because of that. It's standard procedure. Now our graph should start here below 0 because we're going to have our negative vi. This is where it's going to intercept the y-axis, right? That's our y-axis. Remember that this vi occurs when the time is 0. So that means when t is 0 here, we get this point here. And we're saying this line should be a line that goes up. And obviously the line starts here and it goes like that. So this means the point v0 and vi is here. Remember, this is a point 0 and vi, right? It's like a coordinate. I don't know, you can think of it as if it's a coordinate 0 and vi, negative vi. Because we're saying the time is 0 here, we get the point vi. Now our graph will start here and go upward like that. Maybe if I could try to draw it so that it is symmetrical. Yes, let's go with that, so that, because you know the symmetry, the two sides must be the same. Now if we interpret this graph, you would be able to see that when the time is 0, we get vi. When we go to another time here, we get vi. We get v1, I mean to say here, we get a velocity that is getting smaller and smaller until we get to 0 here. This is the maximum height. Then as we continue with our time, it increases, the projectile changes direction. It goes to the positive direction now and increases its velocity from 0 to here. As we do that, it also increases its velocity until it gets to the velocity that it started with. So here what we have actually is that here it will be the time at the maximum height, and this here will be v max, because that's where we are at the maximum height. When we reach this time, the velocity is 0. And here we are going to get t total, because that's where the motion ends. Meaning it will give us the total time from where we started measuring our time to where we stop. Is the total time of the entire motion. This total time will then define the velocity here vi to be positive, because we will have the same speed, right? But the velocity would point in the in the positive direction, because it started in the negative direction. Again, in this case, you would also see that this represents upward motion and this represents downward motion. The only difference is the direction here that has changed. And that's all that there is to drawing velocity versus time graph. Other aspects is the fact that the time is the same to get to the maximum point and going down. And we have already talked about that, to say the total time will be twice the time it takes to go to the maximum height. Let us look at the different scenario by going through question 2. Question 2 says that a ball is thrown vertically upwards with an initial velocity vi from the edge of the balcony. So we have, and then falls back down. eventually it strikes the ground. Take the balcony as the reference point, and then they say ignore the effects of air friction. So in this case, the ball actually goes up, comes back to where it started, and then it passes that point and goes to the ground. Now they say draw the velocity versus time graph for the ball. Take down as negative. Now that means if we draw our direction here using the reference frame, up should be positive because down is negative. When this is negative, this should be up. They are opposite directions. Now that means if I were to draw the velocity that I'm given here, the initial velocity would be VI, and it will be a positive velocity. This VI will be a positive velocity because it's a velocity that makes the ball to go upward. It's the one that makes it to start moving to go upward. So it is in the positive direction. And the other thing is that there is the acceleration due to gravity here, which always points vertically downwards. Okay, my vector doesn't want to be straight. Okay, there it is. So now we have here negative 9.8 meters per second squared. It's a second squared there. Because it goes in the negative direction, it goes downwards, it goes in that direction. So now this means our slope is actually negative because the acceleration due to gravity is the slope on our equation. And this also means that our y-intercept will actually be a positive VI. Based on this information, we can see that our graph should be a graph that goes downhill like that. Because our slope is negative, so the graph should go downhill. And it should start here at the point where we have positive VI as the y-intercept. So this would be where the graph will intercept our y-axis. It should be on the positive side of our axis because it is a positive y-intercept. Now I'm going to take this, put it on a graph now. We are doing question 2.1. 2.1. We are drawing a velocity versus time graph. Now here we have our velocity in meters per second. We also have our time in seconds. This is 0 here. We're saying the graph will start here, it will intercept here at the positive axis, and it's actually going downwards like that. Now, the other thing that we have to notice is that when we come to this point here, I'll call it T, you will see that we will have negative VI, will have the same velocity as the same speed as we had when it was going up, except now it's going down. It becomes a negative velocity. So that is from here to here. So this is this point here. We have negative VI. But this object actually goes beyond this point. It actually then continues to go downwards. You know, it will occupy some position here, some position, and get to this position. So obviously it will have some velocities that are negative here, and another velocity that is negative here, you know, and another velocity that is negative here as it goes down. So that means it will continue a little bit beyond the balcony. So this will be the balcony. It will continue a little bit beyond the balcony and go downwards. And at this stage, that's where we will measure our T total, because it's where it's going to end. We will have some final velocity here which is negative. You know, when it gets to this point here, we will have some final velocity VF which is negative, because that's where it's going to stop its motion. Now, this point we know that it is T max. It is the time at the maximum height, because this time will give me a zero velocity. It will give me a V max. And as usual, this represents the upward motion, and this here represents the downward motion. The only difference is that we get to the balcony and we further go down. That's why this side is longer than this side here. But you must notice that this part here and this part here are still symmetrical. They're exactly the same. In other words, the time it takes to go up is the same as the time it takes to get to the balcony. But now if you continue coming to this part here, it is not the same anymore. It's an additional part of motion here. So only this part and this part are the same. But this part here, it is not the same as this whole part. Very important to notice that, especially when we are going to solve problems. I will jump to question 3 and leave question 2.2 for you to practice this method. Use this study guide to see if you get the same answers that are on the study guide. To get access to the study guide, go to the description of this video and click the link where you will get access to download the study guide and have a PDF version of the study guide. It has answers that you can actually look and check if you are in the right path. If you happen to struggle drawing these graphs, you can leave a comment for me so that I'm able to explain the questions that you struggle with. Question 3 says that a ball is thrown vertically upwards with an initial velocity vi from the edge of the balcony, and after reaching the maximum height, it returns to the balcony. Take the ground as the reference point. Ignore the effects of air friction. Now this question is the same as question 1 if you recall question 1. The difference is that the reference point is now the ground. It is not on the balcony, because in question 1 we said the reference point is here on the balcony. Let us see what happens if we change the reference point. Now here what you'll have to note is that the question 3.1 says draw the velocity versus time graph and take down as negative. So we are saying that a vector that goes down here is a negative vector. So the y is negative there. Our initial velocity will go vertically upwards because the ball goes upwards, so we have vi, which is going to be positive, and our acceleration due to gravity, it has to be sort of a vertical line that goes down. Good. Is going to be negative 9.8 meters per second squared, because it goes in the negative direction, it goes downwards. So this is positive because it goes upwards. Now this means that I have my slope to be negative, and that means if the slope is negative, my graph has to go downhill, and my y-intercept is then given by a positive vi. In other words, it cuts the y-axis in the positive part of the axis. So here we're going to have a point vi which is positive. Now when we put this on our axis, we're going to have the velocity versus time graph, and we actually have here v, which is meters per second, and we also have here t, which is measured in seconds. Now we are saying we are going to plot the y-cut to be vi, which is positive, and our graph goes downhill because the slope is negative. So it will be a graph that goes down like that. You will then observe the fact that when we are at this point, we have T max, meaning is the time at the maximum height, because we are actually going to record here, a velocity of 0 here. This is the velocity at the maximum height. So this is the velocity when the projectile gets to this point. And that actually represents the upward motion here. And here is where the motion will end. We'll have T total. So that's where the projectile actually comes back to where it started, and it has the same speed that it started with, but in the opposite direction. So our velocity is negative here, but our velocity is positive here. So this is when the projectile comes back here. It will have the same speed vi, but it will be in the negative direction. So the velocities have the same magnitude, but point in the opposite direction. And this is because of symmetry. This projectile accelerates at a constant rate. It changes its velocity at a constant rate. That's why the velocities at every point when it goes up, the speeds when it goes up are the same as when it goes down. Now, this represents the downward part of the motion. When you look at this curve, it is exactly the same curve that we drew in question 1. If we go to question 1, you will see that it is exactly the same curve here. It starts at V initial, goes down, you have all that V initial. Okay, here it's detailed because we were trying to explain and make sense out of it. I mean, at this stage we are now rolling, right? But we get the same sketch. Starts at V, goes down, you have V initial there. It's symmetrical, the time it takes here is the same as the time that it takes to go down as well. So what are we learning here? We are learning that even if we change the reference frame, even if the reference frame is the ground, is no longer the balcony, because in question 1 here, we said the reference frame is here. It's the same motion here, but the reference frame is here. Now, with question 3, we're taking the reference frame to the ground. So when the reference frame is the ground, we still get the same position versus time graph as we did when the reference frame was in the balcony. Now, this is a very important observation. If we look at our formula that we use to draw this graph, which is a straight line formula here, we said, we can see that the position or displacement is not part of this equation. In other words, the change in y is equals to y final minus y initial. It's not available in this equation. That is to say, our velocity here does not depend, is independent of the displacement or the positions, because remember, this would be the final position, this would be the initial position, and the whole thing is a displacement when you find the difference between the two. So this velocity does not depend on it. That's why even if we change the positions, we changed the positions here. We removed the position reference point here, and we now took it to be the ground. Even if we change it, we are changing the displacement here. The velocity won't change because it does not depend on the displacement. Very, very important, because if you would remember when we studied position versus time graphs, when we change the reference frame, when we change the positions and displacement, our graphs also changed. They looked different. We sketched graphs that looked different. But for a velocity versus time, it does not have any effect because it is independent of the displacement. I think I've said a mouthful on the velocity versus time graph. However, I have further questions to give you more practice, but I'm not going to do these questions. I'm going to leave them to you to practice because, they give you different scenarios where we change the reference frame and so on. Attempt these questions using the method that I'm sharing with you and let me know how it works for you. Are you able to get the same sketches that I have on the study guide? If you are not able to get the same answers, let me know so that I can do a video where I share how to solve these graphs.